Ok, iniziamo. So today it will be mostly the reviewing of the experiments that I left you to do on Thursday, and we will discuss the theory related to that. I've uploaded on Saturday morning my notebook solutions, and does anyone have any question about my solution or comments about what they did or comments about the results? And do you want to go through the code or shall I go directly at commenting what we are getting? Okay, so I'm going to show you some images. And first, I have tried denoising 3 different levels of noise, some starting from some noise which starts to be already a bit and going to some very high level of noise. And I've tried denoising with the data and the model that I've put in my solution, which is a 50,000 parameters network, which is extremely light. And it was trained on 1,600 slices of brain MR images. And also, I've used the GPUs that I have on my server and I've built a bigger network with 2 million parameters, and I trained it on 55,000 images. So this is the highest level of noise that I have. And on the top, it's the results that I get with the small model, the 50K parameters model, and then with the large model. Now, you can see that this is pretty good, considering that this is the input. However, it's very smooth. It's much smoother than the input image, actually. And one thing that you may notice is the edges are a bit blurrier. Then I've tried with the lower level of noise. And the image gets improved. Indeed, here you can recognize this sulcus between the gyri. You can recognize many of them. These are extremely well defined. And the quality is a bit higher than in the small model, but even here the quality is not that bad. While if you start from the images with the low level of noise, you can see very good quality in both models. And actually, I don't know how effective this is in a projection, but you can see that you get a very high definition here. And especially if you start flipping between the slides, you can really, really see the change in the definition of especially of all the minor details that you get when the level of noise in input decreases. Now I'm doing the same. Oh, sorry, I'm zooming in on the same image, and here you can see it much more clearly how we get here we have some kind of an invented sulcus, which with less noise in input actually is absent. I mean, it's not as a different shape, and this is with the least amount of noise, you can see a proper shape. You can see all the gyri of the gray matter being reconstructed much better and especially much sharper. Now I'm trying on a T2 image. T2 images have a pretty high contrast for the cerebrospinal fluid, actually, which is mainly made of water here. So they get the noise quite well, even in the high noise input image. And again, you can see when the noise decreases that many features get much more detailed and less blurry. By the way, this input image here, for some reasons, had some minor artifacts, maybe due to interpolation, and they disappeared in the denoised images. Of course, I'm using some unseen images to test it. And you can see better on the zoomed-in version what I was saying about the spatial resolution that you can, on the better amount of details that you get. Oops, sorry. When you get to the lowest input noise. So I'm getting images in output that are somehow, they look like they have the same amount of noise, but they have different amounts of blurring. It's not like my denoising neural network is giving me in output images with higher noise the more noise I have in input. It's doing some kind of other thing. Now, here I'm plotting two metrics. The SSIM, the structural similarity index metric, and the peak signal to noise ratio in decibel for the low amount of noise on train and testing datasets. For the four different cases, the input images, my large model, my small model, and what happens if I apply some small Gaussian blur. I'm getting, you see, some minor, here we're getting an improvement. We had 30 decibel of difference and 0.6, and I improve it, especially with the similarity index matrix. This goes up to almost 1. With higher amount of noise, I'm starting from 20 decibel, and I get to 35. And please notice how both the denoising models, one with only 50K parameters, which is not even, I mean, in deep learning is not considered even a noteworthy model. It's getting pretty much similar results. And with extremely high noise, we get some improvements. Of course, we are not as well as before. Now I summarize that in a table. We were 15 decibel, 20 decibel, and 30 decibel. We can improve by 10 decibel here. And you can compare that. We have 1 decibel of difference here, also here, and also here. It's pretty consistent. Also the SSIM, we have some second decimal number here. And so the denoising is pretty effective. We can improve our input image by 10 decibels here and almost 15 in these two cases. And so we can think that we are pretty satisfied. Now, what we did here was really not knowing what we were doing almost. We just know, OK, neural networks do lots of stuff. So let's just brute force whatever we want to achieve. Let's try giving input and output, and let's see what we get in output. And the output looks pretty great. Now we are left with these 3 questions. I mean, these are the 3 questions that I can ask myself after seeing the results. The first one is, why do the outputs get blurrier the higher the noise? We can also ask ourselves, why doesn't working with a much bigger model help more? And we can also ask ourselves, why do denoised images, even starting from low noise, look better than the original ones? Because you could see this with little amount of noise that this is my true image, and this one was the noised one. And starting from here, and you can see that it's somehow smoother. Okay, so as I mentioned before, today is going to be just 2 hours, 1 hour and a half, you know. So I'm going to do mostly theory, and we won't have some programming today. From the next lecture on, it will be instead mostly some kind of programming experiences. Now, we will touch the denoising theory, which is extremely interesting, if you ask me. Most of the material here has been taken from this review paper, which is Image Denoising, the Deep Learning Revolution and Beyond, which covers all the theory about denoising starting from 50 years ago. It was published 2 years ago. It's pretty long, it's pretty mathematical, but it's definitely a must-read for those interested in this topic. So let's go back to the beginning and let's define our denoising problem. We have a noisy image, which we will approximate in this case, which can be generalized quite a lot, as an image corrupted by random independent noise with a normal distribution and uniform level of noise in all the image. So we can say that we measure an image y, which is the input image x plus some standard deviation vector. I guess that in data science, this so-called general linear model is something you've seen countless of times. Our denoiser, it's something that, given in input an image, the image y, estimates one image x hat, which will we can estimate as if we take the mean square error between our input image and the true image, it's the expectation of the true image minus the denoised version of our image. Information theory tells us that the best mean square error that you can achieve actually is the expectation in terms of probability theory of your image x given the input image y. Now, this is apparently simple, but probably if you start thinking at it just super quickly, you say, well, what's the expectation of an image? Practically, how do I go about computing it? Now, we can say, OK, we know that the noise is Gaussian. So we have the probability of measuring y, given that the true image is x, is this Gaussian equation. If you want to maximize that, it turns out that your maximum likelihood estimator of your denoised image is the noisy image, which is probably, OK, you say, OK, I'm done. My job here was pretty quick. But of course, that's not really something good. So what you can try with the Bayes theorem, and you say, my probability of having of my true image being x, given that I observed y, is Bayes theorem. You invert that. Is the probability of measuring y, given that x was the true one, times the probability of x, which is the probability of my image being x. We'll come back to that. And you can just simplify this term here, and you say you take out the normalization constants, and it turns out that this probability is proportional to this Gaussian probability here times the probability of x being the true image. You can now apply that in two ways. One is called the maximum a posteriori estimation. You've probably seen that in multiple different applications in data science. So you take the logarithm of the likelihood, and this is the sum of square differences minus the logarithm of this probability p, given some noise level sigma. There is also the minimum mean square error, which is the expectation of x given y, which is defined this way, which is basically the integral of all the possible images over the space of images times the probability of measuring x given y. This is intractable. So even not in this lecture is intractable at all, because integrating over the space of images, you wouldn't know where to start. So what this means is that our solution, if we want to denoise an image, depends on the prior probability of our solution being a true image. Okay, so let's say we go to a picture taken from a camera with 256 level of gray. Not even talking about medical images with float number of intensity values. How many possible combinations of gray levels are there in an image? If you have an image with 2 by 2 pixels, you have 4 billions of combinations. If you have a 4 by 4 pixel images, which 4 by 4 is not even an image, if you ask me, it's 10 to the 38 combinations, and so on and so on. With an 8 by 8 is 10 to the 154. You need to compare that to the 10 to the 80 atoms present in the universe, which you surpass with an 8 by 8 image, and with 10 to the 123 possible moves in chess. However, it's pretty clear to you that a ridiculously small fraction of combination of gray levels in each pixels look as a natural image. The thing is, how do you define a distribution where you can compute anything? Now, the trick is to define a so-called Gibbs energy. It's called energy because you can actually define it as an actual energy. So this is some function rho of the image divided by the Boltzmann constant and the temperature, which makes this comparable to the sigma noise that we had in the other sum of squares before. However, it doesn't make sense to define a temperature at which we're working at, so we'll just dump everything in some constant C. This is a table of all the prior 4 images that have been suggested. So in the 70s, they suggested an energy regularization. It's very close to ridge regression if you think about it. However, minimizing the energy of the image, which means the intensity of the image, doesn't really make sense. I mean, maybe if you're in microscopy or if you're in astronomy and you're looking at the sky, you can say, okay, I want black almost everywhere, so it might make sense to penalize the intensity of an image. But if you're taking a picture of this square or this room, it's not a sensible assumption to say most things will be black. Let's favor a solution where the pixels are black. Why? The next solution, which has been popular for about 10 years, was to penalize the intensity of the vertical and horizontal gradient. We'll see an example about that. And they've been going on and on and on. An interesting revolution was in the 90s, between the 90s and the early 2000s, where they penalized again the gradient of the image. We'll see why in the next slide. But the L1 norm, not the L2 norm. This is a lasso regularization, and it promotes a sparse solution. And then they went on and on with other strategies that all focused on minimizing the sparsity of your solution in some appropriate space. Now, why did they focus on edges, on the gradient of the image? The gradient represents the edges. And so, if you take a look at this image, you can see that the edges in this image are mostly 0. And somewhere they are strongly non-zero. If I add noise to this image, this is my image of the gradient. And so this intuitively makes a lot of sense. Let's say if I want to minimize this quantity, probably I will cancel almost everything that is present in this image. And especially, okay, you can see this on a test image, the difference between the two approaches. This is minimizing this is a kind of ridge regression. So let's minimize the mean square error plus a term which penalizes the magnitude of the gradient, the L2 norm, the squared intensity. The issue here is that the stronger it is, the blurrier my image. However, here I'm penalizing the, sorry, I didn't write beta here. I'm penalizing the L1 norm of the gradient, which is, you've probably seen that. You've seen the lasso regularization in introductory courses. Yeah. And you can see my output. Here it starts to be piecewise constant, my output, which on this test image is especially useful. Now, for natural images, probably there's a limit to that, because natural images rarely are piecewise constant. But it can be useful. So now, why lasso? Because of sparsity. Let's recap this concept. A signal is said to be sparse if it is 0 almost everywhere and non-zero in very few points. Most signals are not like that. You generally don't measure anything in any field you can think of and you say 0, 0, 0, 0, 0, 0, 1, and so on. Like, a signal can be something like that. But if your true signal is this gray signal here, which is super noisy, you probably, even intuitively, you can say probably this is something piecewise constant. So if you work on the gradient of this signal and impose it to be sparse, and you say the gradient of this signal shall be 0 in most elements, in most possible elements, you get a super strong denoising, because this is a very big assumption. It means that in an appropriate basis, which is some kind of latent space, I can represent this very complex signal using extremely few numbers. If my true signal that I need to recover is this one, I can recover it by saying that it assumes 5 intensity levels, and the first one is this, the second one is this, and so on. So this means that instead of needing to describe 2,000 samples, 20,000 samples, I can just use 10 numbers. The position of where when a change is happening and the intensity of the change. So this allows for really massive, if you find the appropriate latent space, you can get massive denoising. And you can see it very clearly here. So if I penalize the L2 norm of my gradient, I want my gradient not to be too big in all the places, which will blur my edges. Instead, if I say I want my gradient to be 0 almost everywhere, it means let it be 0 whenever possible, but when it is non-zero, let it get whatever value it needs. And this gives me an image where my edges are retained and my image is I can get rid of pretty lot of noise. This is not perfect, again, for natural images, because if I say I want my gradient to be 0 almost everywhere, my solution will be piecewise constant. But we can do pretty much a lot of things with it. Now, there is another paper which probably it's not fundamental as like the other if you're interested in this topic, because it's a lot of probability theory about images. But in 2009, people actually started to ask themselves, is the field of denoising dead? Because in the previous 5 years, they got amazing levels of denoising of images with very different assumptions, most of which were mentioned in the table that I've shown you before. And they all got kind of the same level of denoising performances. They proved mathematically with some assumption of probability theory that there was still, at least theoretically, a bit of space for improvement. But from 2010 onwards, until artificial intelligence came massively like today, they were working with diminishing returns. So they got this very big denoising on some test data sets, they had 27 decibels of denoising. Maybe someone got to 27.1, 27.2 on that specific data set, but that's not massive. Now, let's talk about the most generic we can think of artificial intelligence-based denoiser. How shall we set this up? We should get a very large data set of diverse and clean images representative of all the kind of images we want to work with. Then we need to define one parametric denoiser. This means that it can be mostly anything, but it should be described by some parameters, theta. If we think about neural networks, it will be the weight of the networks, the parameters of the networks. Then we need to define a loss, which is a function of these parameters. Again, for your generic convolutional neural network, it's the weights of the layers. And the loss is defined as the sum of over all images of the distance between the denoised image and the input image. Generally use the mean square error, and what you do is to minimize this loss as a function of theta. You find the theta that give you the minimum square error over all your training data set. Now, of course, given the question that you can get is, do we need any of the theory of the previous 40 years of research? Mostly no, but some it's still good to know to interpret the results and to maintain, and especially the mathematical treatment in terms of probability theory is fundamental to understand how the denoiser work. But all the algorithm, the L1 norms and so on, just inform us conceptually, but sadly it's not really as useful anymore. Now, this is a picture from the same review from 2023 about the performance on one specific data set of the denoising performance over the different years with the total variation, which is the name that's given to the lasso regression of the gradient. They could achieve a 27.5 level of denoising. Here in black is all the traditional algorithms, and in blue all the artificial intelligence algorithms. This one is a transformer Bay, the Swin IR. These others are based on convolutional neural networks, and you can see that they could get from a 28.7 of the Shurlet, which was the best one, up to some 29.5. Now, what can we learn from all the past theory? The locality information. In images, the convolutional neural networks and the patches, when you work with transformers, give priority indirectly, because the neural network can learn anything, but there is what's called the inductive prior, so some information are much easier to learn for a neural network, depending on its architecture. And that anyway, you give priority to local inference. Then there is the concept of sparsity. Neural networks promote transforming the image in a compact representation in some latent spaces. Also, the concept of self-similarity, which was used in many of these prior, is again retained today with the use of attention layers that promotes the repetition of some features in many parts of the images. Now, keeping on studying the issue of denoisers told us how we can achieve many other tasks. Now, before that, I've shown you that the maximum a posteriori solution to the denoising problem was to find this sum of square difference between the training and the true image and the measured images with this probability prior of the original image. And but if here I have a linear transformation, my theory still holds the same way. If I have a neural network that is able to learn the distribution of true images, how true images can look like, I can just put here a linear operator and perform what's called image reconstruction. H, a linear operator, can be anything. So blurring, I have blurring or downsampling. The radon transform, which means the sinogram of the computed tomography, or if I have the Fourier transform, these are the measured data by my detector in MRI. This means that I can use my denoising theory with my denoising neural network, plug and play it in my image, and obtain some very high quality images. So this is the case of blurring. I have my image, I downsample it, I upsample it with the linear interpolation, actually, no, sorry, bicubic interpolation, which is polynomial interpolation. I can use another algorithm of some kind of median filtering. Or if I put some neural networks in my denoiser, I can get almost my input image almost as it is, despite having lost all the information. Any questions so far? Now, we've asked ourselves one of the questions that I left you with at the beginning was why is it that when I increase the noise in my input images, my output images look still without any noise but blurrier? It turns out that our neural network is if deep enough and trained well enough, is able to learn the probability distribution of all the true images. And what I'm asking it to do is to give me the minimum mean square error in output. However, let's assume that for 2 pixels of my images, the green line is the line where the true natural images lie on. This is an example for a 2-pixel image, whatever that might be. So if I want to recover a true image, I a natural image, the 2 pixels must be exactly along this green line. Otherwise, the images will not be natural, it's not natural looking. However, due to noise, I measured this red value here. So if I ask my denoiser, any denoiser, independently of how good it is, to recover the mean square error, it will weight all possible solutions by their probability, and it will give me the minimum square error, which will not be a natural image. So the issue is with what we are asking our neural network to do. We are not asking it to recover a natural image. We are asking it to recover the mean square error of all compatible images. Now, if instead of minimizing the mean square error, we minimize the minimum absolute error, we would have gotten the median image instead of the mean image. Generally, this looks slightly less blurry, but the concept will be identically the same. So this is why we cannot get sharp edges outside of very blurry images. If you think again of the image of denoising as a fitting problem, you can see that as a fitting. What we want to do is, sorry, I got lost. If we want to fit, we want to see amongst all possible images, which one is compatible with the measured data. So it's not necessarily an image. It's probably, if what I've measured is here, all these images that lie here are compatible. Maybe my true image was this one, or maybe it was this one, or maybe this one. And so I can just get the mean. However, given that I'm fitting amongst all feasible ones, my training data set will be, I don't know, like in our case, we trained over lots of MR images. So we say given that I know that I want a T1 image, and this subject has a cortex that probably is this thick, and this brain is so small, so it can infer many data. So it starts from being able to recognize really a lot of data that are present everywhere in the images, but not all of them. So probably the exact position of the cerebral cortex will not be present. So this is to remember that, therefore, perceptual quality is necessarily worsened. No, it's not worsened. Worse than the true image. Not worsened, it's better than this one, of course. But it's not like if I was maximizing perceptual quality. How can I don't necessarily want to solve this issue. Because as I said, this is a weighted mean weighted by the probability of all the feasible solution. If I want to get, especially if I'm working in with medical images, do I necessarily want to get one with higher perceptual quality? Because if I'm here and I say, okay, my most likely solution is this one, it makes sense. But if I say, okay, let's get one of these, which one? I don't know which one. I need to sample these, and I need to do some random sampling. Oops, sorry. Now, the way that I can get around this, as I was saying, is to sample one random image out of all the compatible ones and extract one given its weighted probability, given my input. So on this paper that I choose, what they did is getting this image, corrupt it with quite a lot of noise, and what you get in output is this other image, which is slightly blurry. However, if you sample from the posterior distribution, which is, again, that distribution that I was showing you before, given the probability distribution of all real images and given all my input information, what could have been one of the possible true images? And if I use a random sampler to sample one of the compatible images, I get all these images, which are more realistic, less blurry. But you can see in this one, the mouth is open. In this one is closed. The eyes are looking to the left, are squeezing, are open and looking forward, and so on, because each of these images is compatible with my very noisy input. And the way they do this is generally with the diffusion model. You've probably heard of them. Is the one like Dolly or all the other freeware generators that you have on the internet. This is not a topic we will cover, but this is just to mention it to you. So what they're doing is sampling from the posterior distribution. It can be done in multiple ways. It can be the diffusion algorithm or something to that extent, but it's like that. You can see it in other examples. Let's say we have different kind of the image degradation with the true one. And if I recover the image with the mean square error, well, first you get quite good images given your input. In this way, in this image here, we have really low downsampling. This is this is compressive sensing, which is a very amazing feature, which means just sampling one pixel out of the other, a subsample of all the total pixel. This is blocking a part of the image, and this is downsampling. And again, if you do a random sampling of the posterior distribution, like in this case, we don't have the mouth, and you can see it that it's recovered once open, once closed, once open. Here you can take a look at the eyebrows, and they have a different shape, and also the mouth is different every way. And also here, you can see that the eyes have a different shape, the eyebrows are different, so I hope you get the concept. Now, this will be just a comment. You need to remember the difference between discriminative AI versus generative AI. In the discriminative AI, you find the probability of a target Y given the observation X. In generative AI, we do the other way around, the probability of the observation X given a target Y. Of course, you can see that they are extremely strongly related. Let's say I have a picture of a handwritten number. The case of a discriminative AI is I ask my model to look at my picture and tell me what's the probability that it is the number 1. In the other case, I say, okay, I have the number 1. Given a certain picture, what's the probability that this one picture is that of the number 1? And in the end, it's just the usual inversion given the bias theorem. However, again, with images, given that we've seen even just 16 by 16 images, there are infinite combination of numbers, of possible numbers, it could give you the mean of all the images that look like 1, but the mean of multiple images are not necessarily meaningful. Or you can sample one random sample of all the images that are likely. Okay, so any questions about all this theory? If not, we can go to some tricks, a lot of mixed tricks that we need when working in practice with the networks. By the way, you've seen until now that nowhere in all this theory the architecture of the neural network enters. There's nowhere written anything about that, and in the theory, you don't know anything. And there are multiple reasons for that. The first one is that the usual issue that a neural network has been proven that given enough parameters, it can learn any function. So any network, if you're able to train it deeply well enough, should in theory work, and should in theory work very well enough. Now, also for denoising images, especially medical images where you don't want to overdo that, nowadays we don't need that many parameters, that deep networks. So maybe some network give you some 0.01 decibel of better improvement. Some are faster to train, some are lighter. But it's not really super relevant. And also, it turns out that all this theory cannot tell us anything about which network is the best. So with all the possible heuristics on the architecture of the networks, we can maybe get some faster training. Now, one of the tricks is residual learning. What we've done until now was to take a network that, given a noisy image, predicted a denoised image. Why don't we ask the network to predict the noise and then we subtract it from the noisy image? That's mathematically equivalent. So the reason for that is that if your measured image is that way, sorry, I flipped the notation, and the amount of noise is smaller than the intensity of the image, your solution is the loss that you have is that one, if you do this polynomial expansion. And the biggest contributor to the loss function is just that the mean intensity of the image and the mean intensity of the reconstructed image are kind of the same value. But if you tell the network to predict the noise, the loss function focuses exclusively on the noise, which is a totally random uncorrelated shape. Because you see, random noise is white noise is just all the black and white spots. There is no regularity of any kind of that, while in the image you have lots of regularity with a bit of noise on top. So this works equally well, should work equally well as training your original network. However, given that the output is such an uncorrelated, difficult to describe object, generally the training is much better conditioned. It can go faster. You can use faster learning rate, and you can use more levels because the gradient is stronger, so it propagates better. Now, another very cool trick is the so-called noise-to-noise training. Now, suppose you don't have the noise-free ground truth. It's not really evident that you should have it. Let's suppose that we have couples of noisy data. The important issue here is that we should have couples of data. So we have our first measure, which is our true image, plus some noise, and another measure, which is of the same image, plus, again, some noise. Now, I've used two different sigmas here, and I've used the letter D instead of the letter N of used for normal noise. Let's say this is a generic noise distribution with even different levels of noise in the two images, with the properties of having zero mean, however. If I ask my neural network to predict this function here, the minimum of the noise x1 minus x2, the network will be able to learn exclusively the true image if the noise mean is 0, because noise is completely random, so it has no way to predict it from another distribution of noise, because no information about that is contained in the other. So if the noise is truly unbiased, you can train on noisy data and still get perfect denoising. And this is why on our reconstructed image, on our networks, even with slightly noisy images, we were able to get some apparently higher quality. There is another trick, which is called the noise to void, which is even more advanced, and there was some 3 or 4 years ago lot of studies about the neural networks of the noise to X, so noise to whatever type, because the question is, what if we don't have pair data and we have a single image? Can we denoise a single image without any ground truth? So they invented a kind of they called it self-supervised network. What they did is was to get patches out of an image, remove the central pixel from each patch of data from the image, and ask the network to predict the pixel that was removed. So this is an example on microscopy data. And here they show what they could get with this noise to void because we were removing one pixel. And in this case, we had the ground truth, and so we could see where it got. But we could see that it works in cases where we do not have any ground truth. Sorry, this had animation. This is the way it works. You get the one patch. You remove the central pixel. You ask it to predict it, get it in output, and for the same reason, if our noise has 0 mean and the image is free from any, if the noise on the image is free from any pattern, this is a very strict assumption about this network, you get a denoised image with pretty good results. So in this case, they had ground truth, and we could compare the use of a traditionally trained UNet with the noise to void UNet, because the architecture actually is the same. You can see pretty good results. One final trick to learn how to denoise, to get images from the distribution, natural-looking images, like I've shown before, instead of using diffusion model, because it's a technique that is falling a bit out of fashion, the use of generative adversarial networks. What do? You use in parallel 2 neural networks. In the first one, you get a neural network that takes an input, goes into this network, which in this case is a denoiser, but it could have been even another task. And then you train a second neural network, which is a discriminator, that gets in input images from your own network and true images. And it needs to learn to distinguish true images from non-true images, which in this case will be denoised images. What you get here, then you start to train these neural networks in parallel. And what you have is that the denoiser needs to constantly improve not to have its images rejected by the discriminator. And the discriminator learns not to be fooled by the denoiser. And in this way, the discriminator will force the denoiser to learn an image which is so-called on the feasible set of solution, which is the one of natural-looking images. However, as I told you, it's pretty good because when you trained it, it's pretty fast to use. The diffusion models instead need lots of computational power. This one instead is just inference, so it's super fast. However, the issue is that training is very unstable because you don't need to minimize something, but you need to, at the same time, minimize and maximize an objective. So you're maximizing a saddle which is intrinsically unstable, and that's an intrinsic problem, so it cannot be improved by using better maximizers or whatever. And then also, there is no way to influence which of the many compatible solutions will be chosen. As I've told you, there are multiple images that could have been generated by your noisy image, maybe some with an edge 1 millimeter to the left or to the right. And there's no way to influence which of the many compatible images will be chosen. So it's not a random sampling. And often it happens during training that they say the mode collapses, and the network always starts to, the first network keeps on predicting just a single denoised image, which for the discriminator is fine because it's a perfect image, but it's just one. You don't want a random one, you want a specific one. Okay, so this is it for the denoising per se. So I wanted to go quickly, if you don't have any questions, about the topic of direct artificial intelligence image reconstruction, which is, I think it's useful to spend 15 minutes about that. I mean, it's interesting. We have seen with MRs that sample data in the Fourier transform space or CT in the sinogram space. We have said, we can always repeat that neural networks are universal approximators. We know that. So why don't we just get data from the detector in input, even if it's the Fourier transform, and get our image in output, including denoising, image reconstruction, and whatever? We can do that. It's a sensible machine learning approach. We can do that this way. We have this ground truth here. We have our estimate. For an example, this is a CT. This is its sinogram. We get an objective function. We have the measured data. We have an optimization algorithm. And we can include some prior information. We can absolutely do that. The thing is, you need to ask yourself, how many parameters do I need to do that? Let's say we have a linear mapping. How many parameters do I need? Let's say that my measure space is 512 times 512. My image space is 512 times 512. And I have 300,000 parameters in input and 300,000 parameters in output. And the linear mapping that I need to fit, if I want to do this fitting as a machine learning problem, I need to fit some 10 to the 11 parameters. And good luck fitting that. Very interesting perspective is this paper from 1991 from this person who, without realizing that, invented convolutional neural networks. He was trying to reconstruct something that's reconstructed by the by the Radon transform. And he tried to do it with multi-layer perceptrons. There weren't neural networks yet. And what is said in this paper is that I know that my problem has my physical problem has a circular symmetry. So I can say that for each angle at which I acquire the data, my weights of my neuron should be the same. And then he started thinking about all the symmetries in his problem. And he said, OK, I'm going to reduce my 3,8400 times, again, the same weight down to 64 elements. So he was saying, by exploiting the symmetries of my problem, like convolutional neural network do, I can just learn the weight of this neural network and use a multi-layer perceptron to do the reconstruction. And he did the fitting, and this is the weights that the network fitted. And with the dashed line, instead we have the weights fitted by the theoretical weights when you are doing a filter with the filter back projection. We have said that we have a RAM filter. This is the shape of this filter, which is this kind of sinc function. And he fitted the same filter in the end. So the concept is pretty old. In this, I guess, was, if I remember correctly, was 2017. Some people started to brute force this approach with this kind of network that looks like a UNet. For path reconstruction, we haven't seen that yet, but it works like a CT with the random transform. Say, OK, let's take the sinogram. This is like a UNet, but there are no skip connection because it's two different spaces, sinogram and image. Let's say, let's just do the convolution downsampling, a very wide latent space, and reconstruct the image. And it worked. There was this, OK, so this is the scheme. There are 300,000 parameters in the feature space, which is the deeper layer of the feature space. The network included 60 million parameters, which at the time was pretty big. Now not anymore, thanks to the large language model. And it needed 200,000 training pairs of images, but it worked. And by the way, in inference, it was 100 times faster than normal reconstruction algorithms, and also the images had less noise. There was also some other kind of trials, also on PET images, and they trained with either a perceptual loss or generative adversarial network. And this is the kind of images that they got. They also compared it, which something that should always be done in when inventing artificial intelligence imaging algorithms, compare it to many other algorithms. So this is the total variation denoising. This is post-reconstruction denoising, and this is direct reconstruction. And this was done on images with different kinds of different levels of noise, sorry. Now, many people started to use this let me call it brute force approach. This was even published in Nature in 2018. They were starting from data, kind of generic data, that were going to a fully connected network, and then back to an image. And a single neural network with almost 1 billion parameter was, with a single training, was able to reconstruct automatically MRI data, MRI sampled with non-standard techniques, PET images, and CT images. Again, these had 800 million parameters, and it worked only on 128 times 128 images, which is very small, especially for high-resolution imaging like CT and MR. But this kind of demonstrates that if theoretically it can be done also in practice. However, you should ask yourself, do we really need a neural network that learns the physics? Because this network was getting in input some complex number of the Fourier transform and learning how to do the inverse transformations, but we already know that we need to do that, or the random transformation. What we can do is we can embed our knowledge of the physics of the different problems in our neural network, and we can get, let's say, the best of both worlds. When we do a direct reconstruction with artificial intelligence, we need no assumptions whatsoever. We are putting no assumptions whatsoever in our artificial intelligence model. Maybe some solutions will be slightly more likely due to what I was calling before inductive prior of the architecture. It works directly on raw data from the sensor, and it does a very fast inference. However, it's a very complex training because you need billions of parameters. Ignores all of our prior knowledge. We have it, so why throw it away? We are not sure how well they generalize, if they have issues with hallucination, and so on. And they are, of course, specific for the images that they were trained on. However, they also invented nowadays the physics-informed artificial intelligence network, where we can put ourselves the knowledge of the physics and of the data likelihood. It also works directly on raw data, and is able to fit the high-quality references as AI, in the same way as artificial intelligence does. It has low training needs. You can train some networks with tens of data, tens of images. However, in inference, it's still pretty slow. Let's skip this algorithm, the mathematics behind that. What we can do is the so-called unrolled neural networks, which have this kind of structure here. So you work on the data from the detector and on the images, and you have some very small networks working in parallel. You compare the fitted data with the measured data. You put the differences in super light neural networks, like 10,000 parameters. You get the update factor of an iterative fitting algorithm, and you put it on a neural networks that work in an image, and you go and you repeat it multiple times. In this way, you are working both with the physics of the program and also using neural networks. Now, here, again, this is something that I appreciate a lot, is a comparison between many different algorithms, also not all of them artificial intelligence. So we have the signal-to-noise ratio of the reconstructions with filter back projection, that is, the most standard reconstruction algorithm for CT imaging. And you have a noise which is pretty high, a PSNR of 20. With total variation, you already go up to 28. And again, if in FBP and in total variation, you don't have any parameters, you don't have any hyperparameter that you need to learn. And also you have a runtime in milliseconds, but of course, total variation, given that it's a lasso regression, takes quite a bit. Then you can denoise the output of the FBP, and you get an extra decibel. Then you can do the learned primal dual algorithm, which was the one that I was showing you before. and you can get almost another 10 decibel more, and you can see that the runtime is relatively, well, it's acceptable, definitely. It's slower than U-Net denoising on FBP. And you should also see here that I'm using just 200,000 parameters as compared to this neural network, which was using 10 million parameters, which is, again, not even that big. But here, by taking the physics outside of the neural network, I can use much less parameter, and I get much better results. These are the same results for a different kind of test image, and we get here the difference on an object which, this was a phantom of ellipses, and of course the noising a number of ellipses is very easy. And then you can compress that in a super short latent space, and the neural networks are pretty good in doing that. If you have an anthropomorphic phantom, which has lots of features as compared to some test images, you can't compress as effectively, so the gain you get is much less, but still you can get from 33 with FBP to 42 with post-processing to 44 with this kind of physics-informed neural network. So that's it. That's everything that I had for today on this topic. I know it was pretty intense. From the next lecture, we will be more on the applied side. So, any questions or curiosities? If not, that's it for me for today.